Hello viewers, welcome to this new video, and today I will going to discuss the rest part of the direct mapping. So if you did not check my previous video on direct mapping, then just go and check it out, because otherwise you cannot understand anything in this video. Okay, so let's start today's journey. So in a previous video we saw that when processor wants to fetch a word from the RAM, then what is the address length and what are the different parts of it in direct mapping. And today we are going to see that when processor wants to fetch a word from the cache, then what is the address length and what are the different parts of it. Now see, here RAM has 32 blocks and cache is a direct map 4-line cache. Now when processor wants to fetch a word from cache, then what will be the address length for the different parts of that address. Now listen carefully. Here each block consists of 4 words and there are total 32 blocks B0 to B31. So there are total 32 into 4, that is 128 words, W0 to W127. So to address each and every word we need 7-bit address, because 128 equals to 2 to the power 7. It is simple, I think it is clear to you. So the total address length is 7-bit. Now when processor search the word, then first it choose the block within which the required word is present. Thereafter, within that particular block, processor find the required among 4 words. So the first target is to find the block and then find the word within it. So to address 4 words within a block, we need 2 bits of address, because 2 square equals to 4. So I already discussed this part in my previous video. So I think it is clear. So these 2 bits of LSB actually denotes block offset. Now processor finds the block within which the required word present. In cache there are 4 lines. So required block may present in any one of the 4 lines of the cache. So to address the 4 lines, we need 2-bit address, because first we have to find that in which line of the cache the required block is present. So there are 4 lines, and to address different 4 lines, we need 2-bit address, because 2 square equals to 4. So thereafter this 2-bit denotes line. Now there are total 32 blocks and 4 lines in the cache. So there are particular 32 by 4 blocks, that is 8 blocks, which can map to the same line. Why they are mapped to the same line? I already discussed it in my previous video, that these particular 8 blocks give the same result when we apply the formula L equals to K mod n. So in a particular line, there may present any one block among possible 8 blocks. So we need 3-bit address. Why 3-bit? Because 8 equals to 2 to the power 3. So here we need 3-bit address to distinguish 8 different blocks in a particular line of cache. Now there are how many bits we have? There are 3 bits. So this rest of the 3 bits are actually tag. This is the tag. Now what is tag actually? Let's understand. Okay, now one thing, that line is also known as index. So in the question they can give that find the index and block offset. So index or line, that is same actually. So here this is the address format in this case when processor fetch a word from the cache. So this is the address pattern. You cannot alter it, you cannot change it. Okay, the first some bits are tag, then some bits are line or index, then the some bits of LSB is block offset. You cannot alter or change the pattern. Okay, this is the pattern. Okay, now let's understand that what is tag. So I already told that there are particular 8 blocks which are mapped to the same line. So it is the diagram that particular blocks which are mapped to the same line of the cache. Now this is the tag. This is the tag. Now listen carefully that there are particular 8 blocks mapped to the same line of the cache. So here are B0, B4, B8, B12, B16, B20, B24 and B28. These 8 blocks are mapped to the same line L0. So how to distinguish them? That is why we need 3-bit tag in this case. So see this table that for B0 the tag is 000, for B4 the tag is 001, like that, so on and so forth. For B28 the tag is 111. So for different 8 blocks there are different tags associated with them. So that is how we can distinguish between blocks which are mapped to the same line of the cache. So that is the concept of tag. Now let's understand that how processor will fetch a word from the cache with an example. Suppose processor needs W17 word. How processor will fetch it from the cache? So here the total address length is 7-bit. So that is why 17 in 7-bit binary representation. So this is the 7-bit binary representation of 17. And here we already calculate that how many bits are tag, how many bits are line or index, and how many bits are block offset. And in the bracket, I just written down the decimal values of the corresponding binary values. Now see, processor needs W17 word. It presents on the block B4. Now what is the formula of the direct mapping? That is L equals to K mod N. So for block B4, according to direct mapping, if we apply the formula, that is 4 mod 4 equals to 0. So block B4 will map to L0. So block B4 will map to L0 as it is. Okay. So that is how direct mapping works. So here we can see that block B4 is mapped to the line L0. And from the address, we can obtain that also the line or index is L0. So they are matched together. Now let's see that the tag is matched or not. So here we can see that for block B4, the tag is 001. Now let's see what's the tag of the address. So according to the address, the tag is also 001. So here the tag of the line and the address tag also match. Now let's see the block offset. So here W16 is the 0th word, W17 is the 1st word, W18 is the 2nd word, and W19 is the 3rd word. So according to block offset, the block offset is 1. So here we can see that here red arrow denotes that W17 has the block offset 1. So it also matched with the block offset of the address. So here we can see that how direct mapping works, how actually processor will produce an address, and how a block will come inside the cache from the RAM. So here we find a new term, tag. So actually, what is tag? What is the importance of tag? At first, according to the line or index of the address tag is compared with the line tag. If both tags are same, then it is known as cache hit. That is, the required word is present in cache. otherwise cache miss. That is required but is not present inside the cache. Now let's take an example and I understand that what does it mean. Suppose W9 is requested by the processor. So here we know the address length is 7-bit. So 9 in 7-bit representation 0001001. So W9 belongs to the block B2. According to the formula, block B2 will come inside L2. According to the formula means L equals to K mod N. So block B2 will come inside L2. Now suppose presently block B18 is present in L2. You can apply the formula and you can get the same result for block B18. It will also come inside L2. So for block B18, tag is 100. So it is now the presently line tag. And processor generates the address 0001001 where the tag is 000. So it is clear that here the address tag is not equals to the line tag, that is 000 not equals to 100. Hence it is a cache miss because block 2 is not present inside L2. Presently block B18 is present inside L2. So I think you can understood that what is the importance of tag. Actually tag decides, means tag comparison decides where it will be going to a cache hit or a cache miss. Now see advantages of direct mapping. So it is an easy mapping technique and easy to implement. It works fast. You guys already saw that. Only one tag comparison needed to check whether the block is present in cache or not. So according to the address, when we find the tag, we just compare the address tag with the line tag, and then from that we can say that whether the required block is present inside cache or not. So that is the point here written down. Straightforward block replacement occurs according to the formula. So here the formula is L equals to K mod N, and according to the formula straightforward block replacement occurs. So these 3 points are the main advantages of direct mapping. Now let's move to the disadvantage. That is more important than the advantage. Now here I take the same example. Suppose there are a word calls by processor W18, then W3, then W16. Suppose these 3 words are called simultaneously by the processor. Now see what will happen. So the first word call is W18. So W18 is inside the block B4. So according to the formula, block B4 will come to the L0. So it is the cache miss. So it is copied as it is. Now the requested word is W3 and W3 is present inside block B0. And we can see from the diagram that inside cache only line L0 is contained by block B4 and all the lines are empty, and now the requested block is B0, and according to the formula of direct mapping we can get the result that block B0 will come inside line L0. So it is a cache miss obviously, and block B4 is replaced by block B0 inside the line L0. So it will come inside L0. Now the requested word is W16, which is again inside block B4, and block B4 is not present inside cache. So it is again cache miss. So it will come inside line L0. That means the present block is B0 inside line L0, and B0 is replaced by block B4. Now it is available to the processor. So here we have total 3 cache miss. Now see carefully. Here the line L1, L2 and L3, these 3 lines are empty. So when after W18, W3 is required by the processor, then block B0 will come inside L1 or L2 or L3 because they are empty. But according to the direct mapping, it is directly told by the formula that block B0 must come inside L0. So that is why here the cache miss rate is increasing. So that is why the direct mapping is not the best, or you can say that direct mapping is not the optimal mapping technique. So this is the disadvantage. Each block of main memory maps to a fixed location of the cache. Therefore, if two different blocks map to the same location in cache and they are continually referenced, the two blocks will be continually swapped in and out, known as thrashing. This event is known as thrashing. Thrashing increases the cache miss rate. So it is a major disadvantage. So it is also the poor cache utilization if we use direct cache mapping technique. And there is a poor temporal locality. So what is temporal locality? We will discuss it in some other class. So these 3 are the major disadvantages of direct mapping technique. So in the next video, we will discuss fully associative mapping technique. That's all for the day. Stay home and stay safe and wait few seconds. So before leave, please like and check out my previous videos. Click here to subscribe and stay connected with Learning Bytes on our social media platforms. Thank you.